to Nortek Speaker Series. I'm Torstein Pedersen, and I will be the host for today's second installment in a three-part series for turbulent measurements. Today's topic is going to be performance models for Nortek Signature series. So, we're fortunate enough today to have Audun Ramstad, who is a development engineer here at Nortek, and he's been here since 2011. His main responsibilities have been with acoustic modeling and algorithm developments, and this includes the development tools to simulate Doppler instrument performance. He has a PhD from the Norwegian University of Science and Technology. So this is a second part of a three-part webinar. The first one was held a couple of weeks ago by Atle Lorman, and it gives you an introduction and a base, it provides you a baseline for what turbulence measurements are and with Nortek instruments. If you're interested in learning more, I encourage you to jump on to this link here and find this video and play it back and learn some more about it. Today's installment is performance models, as I said before, for the Nortek Broadband Signature series. Later on, we'll have applications of small-scale measurements. Now, we haven't yet determined a date, but please stay tuned to learn more about that. So, I will turn it over now to Audun Ramstad, who is our expert, and I'll give you the controls now.
Thank you, Torstein. So, today I'll be talking about measurement uncertainty in the Doppler instruments, and the outline is going to be, we're going to introduce the topic first of uncertainty in these measurements, and look at the origins of velocity noise. We'll also talk a little bit about the basic processing principles of the autocorrelation techniques that we use. And we'll see how the setup parameters that the user can set up for the 82CP can affect velocity noise levels. And these parameters are velocity range, cell size, and bandwidth. And finally, we'll also talk a little bit about SNR sensitivity. So, but first, quick reminder of what the problem here is that we're discussing today. Atle did give an introduction to the concepts of velocity noise in this last talk, but just go over it again. If you're measuring a velocity, you will see that the measurements are going to look noisy. There are going to be variations. And some of those variations, of course, are going to be natural, actual variations in the velocity, and some are just going to be noise. Even if you have a known flow with a steady velocity that's well known, you will still measure some noise around that level. And in the context of this turbulence measurements, they typically look at a spectrum here. Okay, so where you will see the actual variations in the flow, the turbulence at low frequencies. But then as that energy dies down, that has kind of a linear scaling law in the log plot here, it will die down and you will hit a noise floor. And that's expected to be a white noise, so these variations will persist across the entire spectrum. But they will be visible, most easily visible at the high end of the spectrum. And this, of course, is a limiting factor no matter what you try to do. If you're interested in turbulence here, you want to be able to trace this line as far down as possible before it disappears into the noise floor. If you're just interested in measuring a steady flow, and you will see variations around the steady level, and you have to average over some time to get a precise estimate. And the more noise there is in the measurements, the longer you have to average over. So keeping this noise level as low as possible is always in your interest. And we're going to look a little bit at how that can be done. But first, where does it come from? What's the origin of this noise? Well, let's recap first what we do for in a Doppler instrument. Well, what we do is we transmit a signal that has a known frequency. Okay? And then that signal hits particles in the water and is scattered back. And as these particles move, they will cause a Doppler shift. So that's illustrated here. So here's a pulsating particle here that's transmitting a, let's say, a spherical wave back to us, and it's moving, let's say, in this direction here. So in front of the particle, this wave field is compressed, and behind it, it's stretched because the particle is, moving away from the wavefronts moving in this direction. It's moving towards the wavefronts that are moving in this direction. So, and this is the effect that we're familiar with if we hear a car that's passing us quickly. So if the car is approaching me, I'm over here, and I hear this high-pitched sound from this high frequency here. After the car has passed, I'm back here, and I hear this low-pitched sound. Okay, and the faster the car moves, or the faster this particle moves, the larger the Doppler effect is. So it should be possible then, if I can find how much the frequency has changed from what I transmitted to what I receive. That's the Doppler shift. That holds information about the velocity. I can use that to calculate the velocity. That's what we do. So what methods are available to us then to calculate the Doppler shift? Well, let's look at the very simplest possible example first. If I had just a single scatterer, such as this unsuspecting fish here, I transmit a signal and I receive a perfect copy of that, except for it might be stretched or compressed according to the Doppler shift. But other than that, it retains its form. So I can now look at for the zero crossings, for instance, to calculate the frequency, or I can try to fit the whole function with just this stretching parameter to find the as a variable and try to fit it and deduce the Doppler shift from there. And so in principle, if I just have sufficient SNR, if I sample it densely enough, I can in principle deduce the velocity of this guy here to arbitrary precision. But in reality, our Doppler systems typically work with backscatter from small, zooplankton particles that are dispersed in the water column. So each cell might contain hundreds or maybe thousands of particles. So I get a mixture. So let's say that these are all the particles and they're, returning waves like this. Although each of these may backscatter a perfect copy of the transmitted signal, they all mix. So I have a mixture of all faces. So there's no longer any face information retained. Right. So I can no longer look for zero crossings because I don't know where they're supposed to be anymore. There's no known functional form that I can fit it to. So those opportunities are no longer available to me. So I have to resort to some kind of statistical methods to get the frequency information out of this picture here. So, and by nature, if I have a statistical method, there's going to be statistical uncertainty. That's just the nature of things. So that means that no matter what the SNR is, and no matter how densely I sample, I'll still be left with some uncertainty. There will still be statistical uncertainties in the velocity that I deduce. So what statistical methods are available to us? Well, we're going to talk about autocorrelation techniques. Those turn out to be the most efficient and accurate methods that we can use. But before we talk about autocorrelation, let's talk about correlation. Okay, so correlation is, as I think most people know, a statistical measure of similarity in behavior between two observables. If, for instance, I was interested in the sales of beer in a restaurant that's serving outdoors in Oslo, I would not be surprised if there was a correlation between the volume sold and the outdoor temperature on any given day. So that's correlation. One goes up, the other goes up. One goes down, the other goes down, right? And autocorrelation is to look for such correlations within one time series. Okay, not between two, but between one, right? So if I now take this beer sales example, and I look at this correlations as a function of time delays. Okay, so that means that I take the time series and I compare it to itself shifted over by some time lag. And for instance, with the beer sales, you could probably imagine that you would find a correlation if you try to look at time delays of 1 week, because we expect there to be weekly variations, so that sales go up in the weekends maybe and down on the weekdays perhaps, and that repeats over and over. So if you try to look for correlations within that time series, you'll find that a time lag of 1 week is probably where you'll find the highest correlation. Okay, so what I'm trying to establish here is that autocorrelation in this way is an ideal tool to look for repeating patterns in the data. In other words, to find frequencies, which is exactly what we wanted, right? So I want to analyze the signal that's backscattered to me. I want to find the frequencies. I can use the autocorrelation technique to do that. And mathematically, it looks like this, although it may not be too important right now, but we typically use the symbol R for correlation, tau for this time lag that I talked about, and it can be expressed as an expectation value, so it's the product of this observable at time t and at time t plus the time lag, and then corrected for the mean and then normalized by variance. Not terribly important, those details, but that's how that is. And now if we switch our attention from beer sales to the actual signals that we want to process, the signals, this is something that Atle talked about last time as well. The signal that we transmit are chirps. Okay, and what's a chirp? Well, this is a time scale in this direction, and this is the frequency, instantaneous frequency along this axis. So it's a sine wave where we sweep the frequency from low to high. Okay, that's a chirp. Okay, and then we repeat that. So we have, in this case, I have 4 chirps after that, and the time period is now this large T. Okay, so let's look at the autocorrelation function of this particular signal. That's over here. So on this axis, I have this time lag that I talked about. Okay, and it's normalized so that at 0 time lag, that means comparing the whole time sequence to itself. Okay, that has to be perfect correlation. Nothing can be more similar to itself than itself. So we normalize that to 1. And then we find that whenever we move over by 1 period, so here's now one period, we'll find a peak value. That's because we have then reached a situation where we've shifted over so that I'm comparing maybe this chirp to the next chirp, okay? And we've shifted the sequence by exactly 1 period, so I expect to find a high correlation, just like those beer sales when I've shifted it by a week. And if I shift it again, I find another peak at 2 transmit periods, another peak at 3, and then this 4th one is 0 because now there's no more overlap. That's the end of the signal. And so the important point here is that this peak occurs at the transmit or at the period of the signal. So if this period is changed, okay, if it has been subject to a Doppler shift, it means that this sequence here has been either stretched or compressed, which means that this time t here has changed, which means that the position of this peak here has shifted. Okay, so I know what t was when I transmitted, and from finding the position of this peak here, I will know what t is when I receive. The difference between those is the Doppler shift. That contains information about the velocity. And that's the all-important point from this here. Some details we can go into. There are various processing techniques to find the position of this peak here. One is called just a cross-correlation technique. I think that's maybe the simplest to imagine, where you really just sample the received signal as densely as you can, and you compute the autocorrelation function for several time lags around the expected position, around the transmitted position, this transmitted value, right? And then you just interpolate, maybe using cubic splines or something, to try to find the exact position here, okay? And then that gives you the velocity. A more commonly used version of the processing scheme is this covariance method, as it's called. The details of this are not strictly speaking important, I think, so we do something called quadrature demodulation, which you can read about elsewhere probably. The important point is that in that case, the detailed position of this peak here is contained in the face of a complex autocorrelation function. So we talk about a complex autocorrelation function in that case. And there's a face, which holds the information. So far, we've only, we can imagine now that if I want to use the position of that peak to calculate the velocity, I think intuitively we all agree that we want to have this peak as high as possible above the noise floor. We want it to be as sharp and as distinctive as possible. All right. So So what we're going to look at now is how do we get a high peak? Okay. So here again, I've tried to draw the sequence of 4 chirps. And I tried to look at the situation where I look at computing the autocorrelation at a time lag equal to the period t. So I've taken a copy of it, I've shifted it by t, and I'm performing this comparison. That's what the autocorrelation is. I perform a comparison. So then I'm comparing this unit to that. Now, since I've shifted it exactly 1 period, these are identical. These are identical, and these are identical. So when I'm comparing identical units like that, that has to give me the maximum amount of correlation, right? It can't be any more identical than a copy of itself, right? So, and if we recall, the normalization that we apply is to look at 0 time lag. So that means comparing the whole sequence to itself. So in this case, that would be 1, 2, 3, 4 units, whereas in total, that's the normalization. And then I have 1, 2, 3 units that are identical. So the correlation at the first peak is identical now to the number of identical units that I contribute the maximum amount of correlation. That's 1, 2, 3 over 4, which is the total. So 3/4 is the value I expect for that first peak. In this case, for a sequence of 4 chirps. If I go back, I can see that here. Well, this is 0.75 approximately, so that's 3/4. The next one is at 0.5 and then at 0.25. Which then, of course, if I shift it 1 more, there'll just be 2 identical units, and 1 more again, just 1 identical units, still over 4 total units. But primarily, we're interested in the first peak. So I arrived in if I have n chirps, n minus 1 over n is the correlation peak value at that first peak. So that means I can achieve a high correlation by just making this n large, right? Which again can be done by having a longer pulse, just adding more and more chirps. That means having larger cells and having a reduced spatial resolution. So that comes at a cost. The other way is to make this t shorter so that I can fit more chirps into the same cell size. That's equivalent to making the velocity range longer. And that also has some consequences that we will look at later. I also said that it would be beneficial to have this autocorrelation peak as narrow as possible. That actually is the same as having a wide bandwidth. So far, we've just talked about, we've tried to analyze the signal that we transmitted and look at the properties of that. So what now of the signal that's backscattered from multiple particles in the water column? Okay, so I've tried now here to illustrate a cell. This is the width of the cell. And in this cell, I've put several copies now of the transmitted signal. So these are echoes from different particles now, okay? And I made the cell size approximately equal to the length of the transmitted pulse. And that makes sense because this length already dictates the spatial resolution. So it doesn't make much sense to make the cell size much larger or much smaller than the transmitted pulse length. So here are the echoes from different particles. We'll notice that only a particle that's, most of these particles now are split between 2 cells, okay? So this one here has partial contribution into the next cell and a little bit into this cell. This one is partially into this cell and then into this cell. And only the particle that's right dead in the center will contribute its entire signal within this unit cell. So, and I think one point that we should make is that once the overlap with the cell gets to be 1 chirp or less, it's not going to contribute anything to the correlation. That's because if I shift this one over now by 1 time lag, there's no overlap, there's no comparison, so there's 0 correlation, right? And that allows me actually to let cells overlap, okay? I can make this previous cell here stretch all the way into the cell and overlap by 1 chirp. That way, I take care of, this whole signal now belongs to the previous cell, and since it contributes nothing to this cell, I don't count information twice. I just make sure I don't throw away anything. So typically, we try to make the cell size one chirp longer than the transmitted pulse length. So then, with that, I'm ready to try to make a statistical model. Okay, I can look at, as a function of the position here, how much does each particle contribute to the correlation, and then I can calculate an expectation value. If I do this very simply with just a 1D model and assuming that the cell size is exactly one chirp longer than the transmitted pulse, I will find that the nominal correlation, this is the expectation value, so on average, I should expect that the best I can achieve for correlation is this value here. So that's something that we refer to as the nominal correlation. That's something that the firmware calculates for the user. And this is the value you need to compare to if you're trying to look for, quality assessment of your data, for instance. That's the nominal correlation. And it has a simple form. In the firmware, there's slightly generalized, but I think this is good enough to know. And we'll also notice that it's pretty similar to the correlation that I just derived for the transmitted pulse. Only this is n in the denominator has changed to n plus 1. Okay, so still, it makes sense to make the more chirps I add to the transmitted pulse, the higher the correlation I should expect. So now, let's look at scaling with the velocity range, which is also something, it's a set of parameter that you can change in the, when you set up the instrument. When we're using this covariance method that I talked about, I said that there was such a thing as a phase. Okay, so in this is the autocorrelation phase now, phi, which holds the information of the precise position of the correlation peak. So I then have a really simple expression for the velocity. It scales with the sound velocity in the water, this phase, and under here is 4 pi over this f0 is the carrier frequency of the signal. T is again the time period, so the length of one chirp, and those can combine to form the velocity range. Okay, this is just the velocity range times this phase over pi. Now, by very elementary statistics, since these are constants, the standard deviation of the velocity will just scale linearly with this velocity range, and also, of course, it'll be proportional to the standard deviation of this phase, which is a complicated matter to calculate. But when we're talking about scaling with velocity range, we should expect linear scaling, which may seem to contradict something I said previously, because what I said before was that if I just made this period short, I can fit a large number of chirps into my cell. A large number of chirps should give me a high correlation. A high correlation should give me low standard deviation. But what I'm saying now is that if I make this time period low, it's in the denominator over here. It's going to make my velocity range large. And a large velocity range is going to make my standard deviation high. So there must exist some kind of a competition between high correlation and low velocity range. So who wins? And at this point, that's as far as we can go with just very simple math like this and hand-waving arguments. We have to do some actual heavy calculations, right? So we have a simulation model. So this is now for some results for a Signature 1000. I've already decided in this case that I want 0.5 meter cell size. Okay, that's appropriate that's an appropriate length scale for the phenomenon I'm interested in studying here, let's say. So along this axis, I just have the velocity range, and here is the standard deviation, velocity standard deviation. So this looks a little bit complicated, but let's try to sum up what we're seeing. So at least piecewise, I am seeing this linear behavior. I mean, this line here, it looks linear. This line looks linear. So at least for these segments, it looks like we do have linear scaling with velocity range. But I also have these discontinuities. So what happens there? Well, that's where the correlation comes into play. When I start with a very low velocity range over here at this end, that means I have a long chirp, right? So So in this case, with a 1/2 meter cell, there's only room for 2 chirps in the cell right here. But when I make the chirps shorter and shorter, I get to a point where all of a sudden I can fit 3 chirps in. Okay, and when I have 3 chirps in, the correlation makes a jump. So right here, correlation wins. Okay, and then I have linear scaling again until I can fit 4 chirps in. Okay, and then 5 and 6 and so forth. So that's the explanation for this behavior. And in the big picture, you can say that, you know, lower velocity range is better. You know, looks like we have this roughly linear scaling over the whole thing. But locally, if I know that I'm going to have a velocity range somewhere down here, it might be better to fine tune a little bit. And I might find that I can actually gain a lot from going to from here to here, say. So luckily, this isn't something that you have to calculate because this numerical model now has been incorporated into the deployment software. So we can take a look at that. This is a screenshot from the deployment wizard. So this is a setup again for a Signature 1000. We're trying to do turbulence measurements in this case. So I've made a number of choices, and here I can set the cell size right here. So in fine steps. And I've already made a lot of choices before getting to the screen. So that's resulted in a velocity range right here of 2.5 meters per second. And then this model automatically calculates for you the standard deviation. That's presented as a value in the horizontal and the vertical. Now, I think last time Atlas showed how these transformation matrices are applied to the standard deviation, so that that gives an explanation for why it's different in the horizontal and the vertical. So if you want to check that out, you can go back and see Atlas' last webinar. But anyway, it's strongly advisable here if you to play around with these parameters, to see if you can get what's the best compromise between the lateral or the spatial resolution you want, for instance, and the resulting standard deviation that you're going to get. Okay, so let's turn to SNR. Well, if we add noise to a signal, the noise does not correlate, right? So it should be expected that if you add noise, the correlation deteriorates, and that's what we're seeing here. So this is, again, I'm just trying to zoom in on the that first side peak for that 4 chirp sequence. So this is just a transmitted pulse now that I've added noise to. So up here, it peaks with 0 noise. It peaks at 0.75. Okay, this is not, statistic. This is not from multiple reflectors. This is just the transmitted pulse. And then I add noise at 16 dB, 9 dB, 4 dB, and you see the correlation value coming down. Not too unexpected. So that means that towards the end of the profile, when the signal gets weaker and weaker, at some point noise is going to play a bigger and bigger role, and it's going to become noise limited. And so we have a simple rule of thumb that we say that once the correlation has dropped to 50% of its original value, to its 50% of its nominal value, then you're good until that, and after that you have to apply some judgment. So let's take a look in practice. Here's an example where I have 2 panels. Where in both cases I show the range here along this axis, and in the upper panel I have the amplitude in decibels that drops, and then I have the correlation, which for the first part stays flat. So this is the nominal value for this particular setup. Okay, a value around 50, and it stays flat in this portion here where the system is not noise limited, and then there's a transition to a noise limited system, and that, of course, in this lower panel is the standard deviation, which of course also stays flat in the beginning and then starts to take off as the correlation drops. Now let's just check out this 50% rule of thumb and see how that pans out. So I said I started at a value around just below 50 here. If I go to something like 25, something like that, I try to follow that line, see what happens, and I see, oh, well, okay, that's roughly when things start taking off here in the standard deviation. So it depends a little bit for what your tolerances are, but 50%, this rule here, pretty good. And the correlation value is, of course, also given with each ping you get. So you can also use it for a quality measure. If you have some really dodgy pings, it will have a really bad correlation, and you might filter those out. That's another way of using the correlation value. So is there anything then to be done about SNR sensitivity? Can I do anything to improve that sensitivity? Well, it turns out it might be possible. One thing we have seen now is that there are two ways of achieving a low standard deviation. Right? One is a low velocity range, and the other is high correlation. So I can say that, well, the standard deviation scales linearly with the velocity range, and then there's some function of the inverse correlation there. So velocity range now, it's just a constant, right? So if I add noise, nothing happens to that. But correlation will deteriorate with noise. So if I have a choice of how to achieve my low standard deviation, it might be better to lean on having a low velocity range rather than high correlation, because correlation is not going to last throughout the profile. So I've calculated an example here to illustrate this. This is again for a Signature 1000. I have two setups. The blue line is for a very low velocity range of 1.2 meters per second. The red line is for a high velocity range of 5.2 meters per second. The cell size is in both cases around 1 meter. This one's 0.8 and this was 1.2 meters. And that's been tuned now in order for these to perform identically at high SNR. So SNR is along the scale, standard deviation along this scale. At high SNR, they have exactly the same standard deviation. But as I add more noise, you can see that this red curve takes off sooner than the blue curve. All right, and that's, if you try to look at where they take off, there's a difference in maybe a 4 dB. So I've improved my noise tolerance by about 4 dB, which for a 1 megahertz system, depending on the water temperature, roughly 5 meters. So I can extend the range maybe by 5 meters by going to lower velocity range, if that's permissible. I mean, you have to expect to have low velocities there. If you set the velocity range too low, you're going to struggle to correct for ambiguity jumps in your post-processing. So finally, scaling with bandwidth. Okay, we said initially that wide bandwidth is going to cause a narrow peak in the autocorrelation function, and that should be good for determining the precise position of it. Turns out we have a pretty good approximation to say that the standard deviation scale says 1 over the square root of bandwidth. So we want just to make an illustration of that. We have this really wide bandwidth composite transducer that our people at Nortek Pizzo in Aberdeen have made for us. We've made an instrument where we can test this. We can test it with the standard chirp of 25% bandwidth and with an extended bandwidth, 50% bandwidth chirp. So we doubled the bandwidth. So let's look at the spectra again. So again, this is again the velocity spectra. Only this is a linear scale, and I've scaled it so that it's now showing standard deviation rather than just power. Okay, so if I look at the red spectrum, again at lower frequencies, I'm seeing the turbulence coming down. Then I see this peak over here, which is probably some wave information here, and another wave component at this frequency here. And then at high frequencies, the noise floor. Okay, so I've drawn this line here. I can find this is the standard deviation then for this red curve with a 50% bandwidth. Now, when I go through half the bandwidth, I should expect an increase by the square root of 2 in the standard deviation. So this blue line here that I've drawn here is just this one multiplied by a square root of 2. And we can see that fits the data reasonably well. Now, at the high frequency, this blue curve wasn't sampled as densely as this red one. So unfortunately, we don't have all the information up here. But we can see that we do seem to hit the noise floor down here and also over here. So I think it's fair to say that, the noise floor probably is about here for this blue curve. So this shear scaling law seems to hold. So I think that's what I wanted to tell you today. And I don't know if there were any questions.
Yeah, there was, in fact, one question that popped up during this. This comes from Hamish Kerr, and that is a chirp a fixed time period, or is this something that can be altered?
Oh, the chirp time period, yes. That's by changing the velocity range. You change the time period of the chirp.
Okay, so it's an indirect change.
Yeah, it's inversely proportional. I think if maybe we can go back a little bit and see the expression.
Step aside.
Okay. Let me get back to further here. Okay. So I said the velocity range is just equal to now. Okay, so it's the velocity of sound velocity in water over 4 pi f, the frequency, and here t, this is the length of the chirp. Okay, so the velocity range is inversely proportional to the time of the chirp.
Okay, thank you, Audun. I appreciate that. And I'll just say take it one step forward, and we'll just a reminder is that the next webinar, it will be the last one in this series, and this is applications of the 82 CP for real life turbulence problems. So please stay tuned, and thank you for joining us.